CRC. So now in this class, we will start with the pulse code modulation. PCM, that is pulse code modulation. Pulse code modulation. Okay, இந்த நேம்ல PCMல pulse code modulation அப்படின்னு ஒரு கொடுத்திருக்காங்க. In general, modulation means we have to transmit a particular information to a longer distance. But here in case of PCM, we will not be sending our signal to a longer distance in PCM. So the main point you have to understand here, that is PCM is not a modulation technique. Okay, and the name maybe the kuduthirundha kuda PCM is not a modulation technique. PCM alone I am telling. PCM mattum vandu oru modulation technique illa. PCM is not a modulation technique, that you have to understand first. Because whenever there is a modulation, we have to use carrier and all, but here we will not use any carrier. Then what is PCM? PCM is the representation technique. Okay, it is the representation of analog signal in digital domain. So it is the representation of real-time analog signal. Real-time analog means signals will be varying continuously. It is a representation of real-time analog signal in digital domain as a digital data like ones and zeros. It is a representation of real-time analog signal in digital domain, because you should not get confused with the analog to digital converter. Okay, in the measurement and the instrumentation, we'll be studying analog to digital converter, or otherwise in the LIC subject, we may be studying analog to digital converter. There, at a time, we will be converting one analog signal into the corresponding digital value. Okay, that is the concept of analog to digital converter. But here, in case of PCM, continuously we will be converting the analog value into the corresponding digital value. So you should know the difference between the analog to digital converter and then PCM. Again, the PCM definitely it will involve the analog to digital converter also. Analog to ADC is the one part of PCM. Okay, ADC is the one part of PCM. Okay, so PCM is not a modulation technique. So it is the representation of real-time analog signal in the digital domain. Then, what are the basic components in the PCM system? Say we are at the transmitter side. Okay, again, it's not a modulation scheme. Still, we'll talk like a transmitter and then receiver. Okay, so at the transmitter side, what are all the components? So the first component is sampler. First component is sampler. So mainly here our idea is, our aim is, objective is to convert the real-time analog signal into the digital data, continuous stream of digital data. So the first one is the sampler. For the sampler, what is the input? Analog signal is the input, analog input. First, the analog input will be passed through a sampler, then quantizer, then quantizer. So sampler will do the discrete operation in the time domain. Quantizer will do the discrete operation in the amplitude domain. You know, analog signal time is also varying, amplitude is also varying, continuous nature. So அது வந்து நம்ம discrete மாத்தணும். So time discrete மாத்துறதுக்கு யூஸ் பண்றது sampler, amplitude discrete மாத்துறதுக்கு யூஸ் பண்றது quantizer. So first sampler, then quantizer. After quantizing, we have to assign a digital value. So that is encoder. That is encoder. Then output of this encoder is the digital data. Digital data, ones and zeros. Digital data. Again, directly you cannot send the digital data. Again, some coding scheme is there, line coding schemes. அதை யூஸ் பண்ணி தான் வந்து சென்ட் பண்ணணும். பட் at this moment you just consider like it's like a ones and zeros. Then whenever we have an analog signal, it will have some maximum frequency that I am mentioning, like FM. It's not a single signal. Whatever FM I am mentioning is the maximum frequency in the signal. Maybe the frequency is spreading from 0 to FM. FM may be anything, 10 kilohertz or 1 kilohertz like that. But in reality, in general, for any general signal, directly we cannot tell this is the maximum frequency in the signal. Say, what I'm telling, say, for example, you take the voice signal. If you see in some books, they will give 0 to 5 kilohertz. In some other book, they will give 0 to 4 kilohertz. In other books, they will give 0 to 3.5 kilohertz. Okay, so there is no clear idea what is the maximum frequency available in the voice signal. But I already told you, most of the time we may be taking this one 0 to 4 kilohertz. That means what? Almost 90% of the 99% of the information will be available from in the spectrum 0 to 4 kilohertz. Remaining 1% of the signal may be available beyond 4 kilohertz. So mostly we'll take 0 to 4 kilohertz. Again, to avoid that confusion, we have to fix what is that value. Okay. So that's why we should know very specifically what is this FM. So again, to fix this FM, what we will do, we will put one filter before sampler. Again, to avoid this confusion, okay, I must be very clear. Okay, what will be the maximum frequency that is available before the sampler? Then only I can apply the sampling theorem. You might have studied sampling theorem. Sampling theorem is Fs greater than or equal to 2FM, sampling frequency. Okay, quickly I'll come back what is the sampling frequency. But here, first of all, you have to fix FM. Okay, so to fix FM, here I will be using one low pass filter. So what I am telling, before sampler, there must be one device. The device is low pass filter. The low pass filter output only will be given to sampler. So what is the job of this low pass filter? So some analog signal is coming. So this low pass filter will fix FM. It will fix FM. So it will fix FM. What is the maximum frequency available in the signal that I am fixing? Okay, you have to fix, because based on that you have to put the sampler. So to fix that FM, I have to put the low pass filter. Or otherwise, if you are not using low pass filter, you do not know what is FM, automatically you will be violating this formula. Once if you violate this formula, okay, so that will create a problem at the receiver side. Okay, that I will I'll tell you later what is that problem. Okay, so mostly distortions will be there. Okay, see, already we are having 1% loss of information. No problem. Once if you follow this procedure, definitely 1% loss of information will be there. But if you do not use low pass filter, what will happen? More than 5% of the information will be lost at the receiver side if you do not use low pass filter. So it is always better to use low pass filter. Okay, you must have a control over that to avoid the distortion at the receiver side. The distortion is called aliasing. The distortion here, it is called aliasing. Distortion is called aliasing. So if you follow this procedure, we will not have any distortion or aliasing. So that's why this filter is also called as anti-aliasing filter. This filter is also called as anti-aliasing filter. This is the example why we are using low pass filter before sampler to avoid aliasing. That's why the name is anti-aliasing filter. Okay, somehow we have fixed what is FM. So here I have to put one low pass filter. Once if I put low pass filter, I should know very clearly what is FM. Before that, I do not know what is FM. Now I am fixing FM. The moment you fix FM, again, Fs you have to fix sampling frequency. What is sampling frequency? Say, I am having some analog signal. It is varying in time. Or otherwise, for simplicity, I will take it as a sinusoidal signal for analysis purpose. Some signal, I am taking some signal, analog signal. Now I want to convert this analog signal into the corresponding digital signal. First of all, I should pick up the sample values. Sample values. So these are all called the sample values. I have to fix the time. So at what time I am taking the sample, I have to So now this will have some time. Okay, say for example, I am between 0 to 1 second. Then how much sample you are taking within 1 second? Okay, see, you can take any number of sample. In 1 second, say once the signal is given, the signal will have some maximum frequency. Okay, anyway, you are in time domain. Now you can take samples. Okay, the sampling rate can be anything. Within 1 second, you can take 10K samples or 100K samples. Then what is the value? How much number of samples you have to take? So that's why they are giving one formula to avoid distortion at the receiver side. Definitely, what is our aim? Analog signal we are representing in terms of digital data. From the digital data, we have to recover back our original analog signal. That is the aim. அப்போ samples எடுக்கும் பொழுது the sampling rate must be at least greater than 2 FM. Fs must be at least greater than 2 FM. Now what is Fs? Fs is the sampling frequency. Okay, sampling frequency. Again, what is the unit of sampling frequency? It is not hertz. I may be mentioning like sampling frequency, but the unit is not hertz. It is like samples per second. So what is sampling frequency? Number of samples taken per second. Number of samples taken per second is called sampling frequency. See, the name may be sampling frequency, but what is the actual meaning? How many number of samples you are taking in 1 second? That is the sampling frequency. That is the sampling frequency. Okay, so Fs. So again, Fs they have mentioned. Say for example, if Fm is 4 kilohertz, for voice signal, I am restricting my frequency maximum to the 4 kilohertz. That means Fs must be 8K. So what is the idea here? I have to take 8,000 samples per second. In 1 second, I have to take 8,000 samples, 8K samples. Okay, if you want to represent this information in terms of digital data, at least you have to take 8,000 samples, but it can be greater than that also. Suppose instead of 2 FM, you can use 3 FM also, but 2 FM is the minimum value. If FM is greater than 2 FM, say for example, instead of 8K, you can take 12K also, you can take 16K samples, it's your wish. But அதிகமாக எடுக்க there will be some problem. அதெல்லாம் நம்ம லேட்டராக பார்ப்போம். So first வந்து நம்ம அண்டர்ஸ்டாண்ட் பண்ண ட்ரை பண்ணுவோம். So Fs means how many number of samples you are taking per second. Say for example, in some problem they are giving example. In a particular conversion technique, PCM technique, they have taken for 0.1 millisecond, okay, 500 samples have been taken. 500 samples taken. Then what is the sampling frequency? Okay, see, they have not mentioned for 1 millisecond. Sorry, 1 second. They are given for 0.1 millisecond, 500 samples have been taken. Then in 1 second, how many samples will be taken? So now, what is the sampling frequency? Anybody? Very simple. Sampling frequency means 500 samples have been taken for 0.1 millisecond. Then once if you do this operation, you will get 500K. So that means per second, 500K samples will be taken. Okay, 0.1 millisecond 500 எடுக்கிறாங்கன்னா அப்போ 1 secondல 500 samples எடுத்திருப்பாங்க. அப்போ what is the sampling frequency அந்த கேஸ்ல 500K. Okay, so 500K samples per second. Okay, again, what is the sampling interval? 1 secondல 500 samples இருந்ததுன்னா what is the sampling interval? Simple, 1 by Fs. So 2 microsecond will be the sampling interval between the samples. Okay, 1 secondல 500K samples இருக்கு. Between the samples, what is the time? Simple formula, Ts is equal to 1 by S. So 2 microsecond. இதுக்கு reverse பண்ணீங்கன்னா 2 microsecond வரும். If you have doubt, each sample will have 2 microsecond difference. You know how many number of samples are there? Okay, say 500K samples are there. Each sample is having the duration of sampling interval is 2 microsecond. If you multiply, you will get 1 second. If you multiply these two, you will get 1 second. That is the simple idea. So now, somewhat we understood what is Fs, Ts, and then everything. Then we'll come here. So now we are defining Fs is equal to 8k, or in general, the minimum Fs, this I will call it as a minimum Fs, that is 8k, or there is another name for minimum Fs, that is the Nyquist rate. That is the Nyquist rate of sampling. Okay, F Nyquist, that is 2 times of Fm. F Nyquist rate. Nyquist rate of sampling means only 2 times of Fm. In general, it can be greater than 2 Fm also. So Nyquist rate of sampling. Now, in 1 second, 2 Fm samples are there. Then what is the sampling interval? Ts means sampling interval. Sampling interval. Or otherwise, see, you can observe here. I have taken samples like this. Now, what is the time difference between these two samples? That is the Ts. Time difference between the two adjacent sample is called a Ts. Sampling interval Ts is equal to 1 by Fs, or it is 1 by Fs means 2 Fm. 1 by Fs means 1 by 2 Fm. So this is the sampling interval between the adjacent samples. இப்போ என்ன பண்ணோம், ஒரு அனலாக் சிக்னல் எடுத்தோம். ஒரு செகண்டுக்கு எத்தனை சாம்பிள்ஸ் எடுக்கணும்னு ஆல்ரெடி ரூல் இருக்கு. ஆர் அதர்வைஸ் நாட் 1 செகண்ட், இன் ஜெனரல் அதனுடைய மேக்ஸிமம் ஃப்ரீக்வன்சி என்னவோ அதுல இருந்து 2 டைம்ஸ் பண்ணணும். ஸோ தட் many நம்பர் ஆஃப் சாம்பிள்ஸ். அப்போ 1 செகண்டுக்கு 2 Fm நம்பர் ஆஃப் சாம்பிள்ஸ், அட்லீஸ்ட் 2 Fm நம்பர் ஆஃப் சாம்பிள்ஸ் வந்து எடுக்கணும். அதுக்கேற்ற போல நீங்க லைன்ஸ் போடணும். இப்போ டைம் டொமைன்ல டிஸ்கிரீட் பண்ணியாச்சு. அனலாக் டொமைனை நம்ம என்ன பண்ணணும், டிஸ்கிரீட் பண்ணணும். அனலாக் டொமைனை டிஸ்கிரீட் பண்ணணும்னா ஐ வில் புட் லைன்ஸ் லைக் திஸ். I will put like levels. This I will call it as a, in general, this is called as a levels. Again, how many number of levels you are assigning? 4 levels assign பண்ணலாம், 8 levels assign பண்ணலாம். Say in this case, I am just assigning 4 levels. So at any point of time, my sample value, either it will be, say, this is level 0, this is level 0, this is level 1, this is level 2, this is level 3. I am having 4 levels. At any point of time, my sample value will be mapped to the nearby level. Okay, either this will be mapped to this level, this sample will be mapped to this level, this will be mapped to this level. So somehow I am assigning each sample to the nearby level. Then what I will do, for each level, I will assign digital bits. Level 0 means 0, 0, level 1 means 0, 1, then 1, 0, then 1, 1. Okay, say for example, I am having this sample, so definitely this will be mapped to level 3. Then what is the corresponding data? Okay, this will produce 1, 1. Again, this sample is also will produce 1, 1. This also will produce 1, 1, 1, 1. Again, this is also 1, 1. But this is very close to level 2. Level 2 means 1, 0. Okay, again, if you come like this, say this will be mapped to level 1. Again, 0, 1. So like this, you have to assign the bits. இப்போ என்ன பண்றோம், டைம் டொமைன்ல டிஸ்கிரீட் நேச்சரை கொண்டு வந்துட்டோம் யூசிங் சாம்பிளிங் ஃபார்முலா. அதுக்கப்புறம் ஆம்பிளிடியூட் டொமைன்லயும் டிஸ்கிரீட் கொண்டு வரணும். அதுக்கு லெவல்ஸ் அசைன் பண்றோம், நம்பர் ஆஃப் லெவல்ஸ். ஜென்ரலா அது வந்து 2 பவர்ல இருக்கும். 4 லெவல்ஸ் அசைன் பண்ணலாம், 8 லெவல்ஸ் அசைன் பண்ணலாம், 16 லெவல்ஸ், இது போல எத்தனை வேணாலும் அசைன் பண்ணலாம். பட் இஃப் யூ அசைன் 4 லெவல், ஈச் சாம்பிள் ஹேஸ் டு பி ரெப்ரசன்டட் பை 2 பிட்ஸ். ஏன்னா டிஜிட்டல்ல உங்களுக்கே தெரியும், 4 லெவல் இருந்தா ஒரு லெவலுக்கு மினிமம் 2 bits அசைன் பண்ணி ஆகும். இதுவே நீங்க 8 levels அசைன் பண்ணிருந்தீங்கன்னா each sample will be assigned 3 bits. 16 levelsனா each sample will be assigned 4 bits. பட் என்ன ஐடியாங்கன்னா, இது நீங்க எத்தனை லெவல் ஒன்னாலும் அசைன் பண்ணலாம், அது ப்ராப்ளம் கிடையாது. பட் ஆனா அந்த பிட்ஸை வந்து அடுத்த சாம்பிள் வர்றதுக்குள்ள டிரான்ஸ்மிட் பண்ணணும். அதுதான் மெயின் ப்ராப்ளம் ஹியர். நீங்க ஒரு சாம்பிளை 2 பிட்ஸை வச்சு கூட ரெப்ரசென்ட் பண்ணலாம், 3 பிட்டோ 4 பிட் எவ்வளவு வேணாலும் பண்ணலாம். பட் நெக்ஸ்ட் சாம்பிள் வர்றதுக்குள்ள அதை டிரான்ஸ்மிட் பண்ணணும். ஏன்னா நெக்ஸ்ட் சாம்பிள் வந்து அதனுடைய ஓன் டேட்டா வரும், அதையும் நம்ம டிரான்ஸ்மிட் பண்ணி ஆகணும். ஸோ இது எல்லாத்தையுமே வந்து நம்ம பார்க்கணும். ஸோ நவ் ஐ ஹவ் இன்ட்ரடியூஸ்டு த லெவல்ஸ். ஓகே, லெவல்ஸ். ஸோ எல், ஐ ஹவ் இன்ட்ரடியூஸ்டு எல். எல் இண்டிகேட்டிங் தி நம்பர் ஆஃப் லெவல். Number of level. So again, this comes under the topic of quantization. This process is called as quantization. So after sampling, we have to assign the level. Okay, that is called as a quantization. That is called as quantization. So L is indicating number of level. For each level, I will assign n number of bits. Okay, bits, number of bits for each sample. Each sample, you can say each sample or each level. Number of bits for each sample, number of bits for each sample, or otherwise level, anything. Anyway, all the sample will be mapped to some level. So you can call it as for each sample or each level. Anything is okay. So now there is a relationship between L and N. If you carefully observe, number of level is equal to 2 power N. Number of level is equal to 2 power N. For simplicity, you see here, I am having 4 level. Again, for each level, I am assigning 2 bits. So definitely 2 power 2 is 4. So number of level is equal to always 2 power N, where N is the number of bits, L means number of levels, number of levels. Again, what will happen if you increase here itself? It is very evident. Suppose if you are trying to increase L, definitely N will increase. Or if you try to increase N, L will increase. அதுபோல L decrease பண்ணா N வந்து decrease ஆகும். So that is the main observation here. Say for example, I am trying to increase N, definitely L will increase. இல்லனா L increase பண்ணாலும் N வந்து increase ஆகும். இதனுடைய ப்ராப்ளம்லாம் என்னன்றது நம்ம லேட்டரா இதனுடைய some problem இருக்கு. இதெல்லாம் increase பண்ணாலோ decrease பண்ணாலோ there will be some problem. இதெல்லாம் அடுத்து நம்ம பார்ப்போம். Okay, so levels இதெல்லாம் வந்து assign பண்ணியாச்சு. Now we'll define quantization noise. Okay, in the process of quantization, say again before that we'll define one more parameter, step size. Okay, step size. Step size means what is the difference between the levels. Say I have assigned 4 levels, then what is the difference between each level? That is the step size. Difference in the levels is called step size. So the formula for step size is dynamic range of the signal. Dynamic range of the signal. Dynamic range means in the value, what is the minimum value, what is the maximum value in the analog signal. Dynamic range of the signal divided by number of level. Where what is the dynamic range? What is the maximum value present in the signal? Then what is the minimum value? Minimum value may be negative also. Here I have taken minimum value as 0 in this case. In reality, minimum value can be negative also. So in general, Vmax minus V minimum then divided by L. This is the step size. So now I'm going to define quantization error. I'm going to define quantization error, quantization noise. Quantization noise. Okay, for that, once again, I'll draw the diagram. Say I'm having some signal. I have assigned the level. Now I am here. When I am here, this is level 0, level 1, level 2, level 3. Again, for simplicity, I will assume that this is 0 volt, 1 volt, 2 volt, and then this is 3 volt. Okay. So now this sample definitely it will be mapped to, see, in reality, this value may be 2.8 volt. But when you do the quantization process, this will be mapped to 3 volt. Definitely this will be mapped to level 3. Level 3 means 3 volt. Now we are at the transmitter side. Now when we go to the receiver side, can we recover back 2.8 volt from the 3 volt? That is the question mark. Can I recover back 2.8 volt exactly from the 3 volt? That is the question mark. So you cannot recover, because any voltage in between 2 to 3 or at least any voltage that is greater than 2.5 definitely will be mapped to 3. At the receiver side, we cannot demap exactly. Okay, so exact demapping is not possible. Okay, only we'll do some kind of approximation, but exact demapping is not possible. So that means voluntarily we are introducing some noise. So in the process of quantization, we are doing quantization. So here we are introducing noise. How much noise we are introducing? Around 0.2 volt is a noise. Okay, because 2.8 you are approximating to 3. Again, from 3 you can get exactly 2.8. That is a question mark. So you are introducing some noise. That noise is called quantization noise. That noise is called quantization noise. So this noise is not coming from anywhere else. The user, we are introducing. Okay, we are in the process of converting analog signal into digital signal. We have to use quantization procedure. But once if you use quantization procedure, definitely some kind of noise will be introduced. That noise is called quantization noise. That is irrecoverable. You cannot recover back. You cannot remove that noise. Okay, so quantization noise not removable. You cannot remove it, not removable. Once if it is introduced in the system, you cannot remove it, but you can try to decrease, you can try to reduce the quantization noise. Okay, we may by means of some other technique, say quantization noise, or otherwise I'll put like quantization error, noise or error, we may try to reduce. Okay, we may try to reduce by using some technique. We may reduce it. We may try to reduce it, but you cannot make it zero. We may try to reduce it, but once if it is introduced, it cannot be removed. Okay, in the system, once if the quantization noise is introduced, it cannot be removed. So that is the main point you have to note down. So in the exam, they will ask whether we can remove the quantization noise or not. So we cannot remove it. Once if it is introduced, it is irrecoverable. You cannot recover it back. Okay, so then what is exactly the quantization noise value? See, I have taken 2.8 volt. So now the quantization error is 0.2. Suppose if I am taking 2.5, this 2.5 may be mapped to 2 or 3 because both are at the equal distance. So definitely this will be mapped to 3 volt or it may be mapped to 4 volt. Or otherwise, suppose if I take 2.1, definitely this will be mapped to 2 volt because level 2 is the nearby. That time, what is the quantization error? Say that is 0.1 volt. In general, how to find out the quantization error? Say that is actual value and then quantized value. Quantized value, actual value minus quantized value. So now my samples can be anywhere in between. Then if you carefully observe in this case, what is the quantization error, range of the quantization error range? If you carefully observe, the quantization error range can be from minus 5 volt to 0.5 volt. Okay, depending on at which value you are at any point of time, definitely the range will be within this only. ஏன்னா மிடில் போயிட்டீங்கனாலே 0.5 தான் டிஃபரன்ஸ் வரும். அப்போ ஆட்டோமேட்டிக்கா ஏதாவது ஒரு லெவலுக்கு போயிடுவீங்க. ஸோ இல்ல சப்போஸ் சாம்பிள் இங்கே இருக்குன்னா குவான்டைசேஷன் எரர் இருக்காது, ஜீரோவா இருக்கும். ஸோ குவான்டைசேஷன் எரர் ஜீரோவா வரலாம், பாசிட்டிவ் சைடு அப் டு 0.5 போகலாம், நெகட்டிவ் சைடு அப் டு minus 0.5 போகலாம். பட் மேக்னிடியூட் வைஸ் இஃப் யூ சி ஜஸ்ட் டு 0.5 volt. Okay, but if you follow this formula, this is from either from minus 0.5 volt to plus 0.5 volt. Okay, this is the range of the quantization error. Now, what is the maximum quantization error possible? What is the maximum? Here itself you can understand the maximum value in terms of value. I am telling the maximum quantization value is 0.5 volt. This is same as step size divided by 2. This is same as step size divided by 2. Step size we will call it as del divided by 2. Why step size? Del. What is step size? Yeah, you can easily understand. Step size means difference between the level. Now, what is the difference between the level? That is 1 volt. So quantization, maximum quantization error is step size divided by 2. Del divided by 2 is the maximum quantization error. Okay. So step size na define பண்ணோம். Step size na difference between the levels, that is del by 2. Again maximum quantization error வந்து possible another del கிடையாது, del by 2 தான் another maximum quantization error. And then one more observation you have to make that we will be using very quickly. What is the distribution of this error? See, what is the distribution? Whether, see, I can get the error, the error range, QE range. The error range is from minus 0.5. Minus 0.5 means I can get minus 0.4, minus 0.3, then 0, 0.1, 0.2, like that it goes. That means I can get any value of error. இப்போ இந்த எரர்ல ஏதாவது நம்ம கெஸ் பண்ண முடியுமா? 0 எரர் தான் அதிகமா வரும், இல்லைன்னா மைனஸ்ல இருக்கிற எரர் தான் அதிகமா வரும், இல்லைன்னா பிளஸ்ல இருக்கிற எரர் தான் அதிகமா வரும் அப்படின்னு ஏதாவது கெஸ் பண்ண முடியுமான்னு பார்க்கணும். ஏதாவது பயாசிங் இருக்கா இல்லையா, இல்லைன்னா யூனிஃபார்மா வர்றதுக்கு தான் சான்ஸ் இருக்கா. when we take many number of samples, say infinite number of samples, what is this distribution, whether this is uniform or non-uniform. So if you carefully observe, this is uniform. This will become like a uniform. When you take many number of samples, what is the error occurrence distribution that will be uniform. மைனஸ் தான் அதிகமா வரும்னு சொல்ல முடியாது, பிளஸ் தான் அதிகமா வரும்னு என்னால் சொல்ல முடியாது, இல்லைன்னா ஜீரோ தான் வரும்னு சொல்ல முடியாது. ஏன்னா here itself you can observe, you are keep on changing the value, definitely error also will be changing within the range. So again you cannot do any biasing here. So the error distribution is uniform. The quantization error distribution is uniform distribution. In the exam they will ask, what is the distribution of quantization error? That is in general uniform. So now almost we have defined all the formulas. Okay, then see, in the beginning we have taken fs. Okay, fs means number of samples per second. That means after applying sampling theorem, in 1 second I will be taking fs number of samples. Then, and I also know how much bits is there in each sample, number of bits in each sample. Then what is my data rate? See, ultimately somehow I have assigned ones and zeros. Now what is the data rate? That I will mention like RB. RB means finally how many number of bits are there per second. That is simply fs multiplied with the n, number of sampling frequency multiplied with the n. What is the unit of this? Bits per second. Again you apply the unit. See, this is number of samples per second. This is number of bits per sample. Sample cancel. So I will get bit per second is the unit. So finally what is the digital data rate? That is n times of fs. RB data rate digital convert பண்ணிட்டோம். கன்வெர்ட் பண்ணிட்ட பிறகு அதனுடைய டேட்டா ரேட் என்ன அப்படின்னு கேட்டாங்கன்னா n டைம்ஸ் ஆஃப் fs. fsனா சாம்பிளிங் ஃப்ரீக்வன்சி, n நம்பர் ஆஃப் பிட்ஸ் அசைன்டு டு ஈச் சாம்பிள். ஸோ நவ் ஐ வாண்ட் டு சென்ட் திஸ் டிஜிட்டல் டேட்டா டு தி ரிசீவர். சே we are in the baseband communication. Baseband means without any modulation, or mostly you can imagine like a computer communication. Now say I am having some device, this is converting my analog signal into digital, then now the output is digital. Say now this is connected to the computer. Now here we no need the complicated modulation and all, directly it is connected with the wire, but this wire also has to support some bandwidth. Okay, now I know what is the data rate, digital data rate. Now what must be the bandwidth so that this will carry this digital data reliably over this wire? Okay, that is another question. So now I know what is the bandwidth. If somebody is asking what is the bandwidth needed to carry this digital data, that is the minimum bandwidth is RB by 2. Okay, please don't get confused with this. Okay, this is valid only at PCM. So in PCM finally we are generating RB, that is n times of fs. Then what is the minimum bandwidth needed? That is RB by 2. Again this formula also will be modified a little bit. Instead of giving like this, sometime they will mention RB by 2 1 plus alpha, because again raised cosine filter is there, one concept there. Alpha will vary from 0 to 1. When you put alpha is equal to 0, that is RB by 2. When alpha is 1, bandwidth is RB. So that's why here I have mentioned bandwidth minimum. So this is possible only when alpha is equal to 0. Okay, if alpha is increasing, bandwidth is also will increase. Okay, so at least please note down this formula. Again, there is the modified version of this formula, that is bandwidth is equal to 1 plus alpha divided by 2 TB, or in general write like 2 TS, or to avoid confusion you can write either TS or TB, but later on you have to understand what is the difference between TS and TB, or at least you write TB now. 1 plus alpha divided by 2 TB. This is the modified version. Okay. So now we know what is RB. RB is N into Fs. Then somehow we know bandwidth is related with the bit rate. So again, forget about this formula and all. Now what is the observation? If RB is increasing, definitely the bandwidth needed to carry that particular digital information also will increase. Bandwidth of the channel has to be increased. Bandwidth of the particular user. Okay, user, because user is giving the analog signal that is being converted into digital data. So definitely that will occupy the particular bandwidth, say user bandwidth. For that particular user, we need this much amount of bandwidth. So once if you increase the data rate, definitely bandwidth of the particular user will increase. Okay, bandwidth of the user has to be increased. And then you should also know the another concept in general. The bandwidth of the channel must be as high as possible. Bandwidth of the channel must be as high as possible. Then bandwidth of the user, okay, user bandwidth of the user must be as low as possible. Bandwidth of the user must be as low as possible. Why I am telling? See, channel bandwidth is the common bandwidth. Channel bandwidth is the common bandwidth. User bandwidth means and the particular user enna bandwidth use பண்றாங்க. So what is the advantage here? See, what is the relation? Then I can define N. N means bandwidth of the channel. Then, sorry, N means bandwidth of the channel divided by bandwidth of the user. See, anyway, channel bandwidth is fixed. We cannot change. Channel bandwidth is fixed. But if you try to reduce user bandwidth, you can accommodate more number of users. That is the main observation here. So what is the observation? In general, we are having some common channel. User is having their own bandwidth. But if the user bandwidth, by using some means, by some technique, if you are trying to reduce bandwidth of the individual user, you can accommodate more number of people. You can accommodate more number of people. Or otherwise, if you are increasing user bandwidth, you cannot accommodate many people. The number of user in the system will reduce automatically. So now we'll come to our discussion. In our discussion, RB is equal to N into Fs. When we increase L, say number of level, automatically N will increase. Automatically N will increase. Then if you increase number of bits or number of level, mostly we will be assigning more number of levels. Okay, more number of levels. Then the clarity of the signal, clarity will be better. Okay, when we take, when you increase N, automatically the clarity will be better. Or otherwise, you can observe this from the quantization error formula. The maximum quantization error we have defined like del by 2. What is del? Del means step size. Step size means V max minus V minimum. V minimum divided by L. V minimum divided by L divided by 2, where what is L? L means 2 power N. L means 2 power N. So what you are observing here, when you increase N, automatically quantization error will reduce. Once quantization error reduces means clarity will increase. So when you increase number of level, or just from the common sense you can understand, just from the diagram you can understand, when you increase number of level, definitely error will reduce, that ambiguity will reduce, confusion will reduce, so clarity will increase. But what is another problem? Clarity may be better, But what is the another problem here? Okay, when you increase n, RB will increase. If RB increases, bandwidth of the user, particular user will increase. If bandwidth of the particular user increase, number of person that can be accommodated in the system will decrease. So what is the problem? If the bandwidth of the each user increases, number of people will get reduced. Number of person that can be accommodated in a particular system will get reduced. That is the major problem. That is a major problem. Say, I will explain this with the real-time example. நம்ம இப்போ ஃபோனில் எல்லாமே பேசுகிறோம். நம்மளுடைய வாய்ஸ் தான் ஃபோனில் பேசுகிறோம் கால் பண்ணும்பொழுது. அதனுடைய மேக்ஸிமம் ஃப்ரீக்குவன்சி வந்து 4 கிலோஹெர்ட்ஸுக்கு ரெஸ்ட்ரிக்ட் பண்ணுறாங்க. அப்போ சாம்பிளிங் ஃப்ரீக்குவன்சி என்னவாக இருக்கணும்? 8K இருக்கணும். சம் நம்பர் ஆஃப் லெவல்ஸ் யூஸ் பண்ணுவாங்க. நம்மளுக்கு யூஸ் பண்ணுற லெவல்ஸ் வந்து 256. அதாவது நம்மளுடைய வாய்ஸை வந்து டிஜிட்டலாக கன்வெர்ட் பண்ணும்போது 256 லெவல்ஸ் அசைன் பண்ணி கன்வெர்ட் பண்ணுறாங்க. அப்போ நம்பர் ஆஃப் லெவல்ஸ் வந்து 256. தென் L is equal to 2 power n. From this, what is n? N is equal to 8. சரி, அப்போ what is the bit rate? Bit rate is n into fs. n na 8, fs na 8K. Then what is the digital data rate? 64 kbps. அப்போ நம்ம பேசுகிற வாய்ஸ் எல்லாமே ஜென்ரலாக ஃபோனில் வந்து என்ன பண்ணுறாங்க? 64 kbps கன்வெர்ட் பண்ணுறாங்க. அதுக்கப்புறம் தான் அதை மாடுலேஷன் பண்ணி ஆண்டனா டவருக்கு சென்ட் பண்ணி, மொபைல் டவருக்கு சென்ட் பண்ணி அதை ரிசீவருக்கு வந்து போகுது. இதுதான் வந்து ஜென்ரலாக நடக்குது எனி டிஜிட்டல் கம்யூனிகேஷன். ஈவன் கம்ப்யூட்டரில் நீங்கள் பேசுறது கூட கம்ப்யூட்டரில் ஸ்டோர் ஆகுதுன்னா டிஜிட்டலாக தான் ஸ்டோர் ஆகும். ஈவன் மொபைலில் கூட எடுத்துங்க, நீங்கள் பேசுறது அனலாகாக ஸ்டோர் ஆகாது, டிஜிட்டலாக தான் ஸ்டோர் ஆகும். பிகாஸ் எனி memory element cannot store the analog signal, because analog signal will have infinite number of information. So with the finite amount of storage device, you cannot store infinite information. So in general, all the storage medium will store only the digital data. So அப்போ நம்மளுடைய வாய்ஸ் சிக்னல் இதெல்லாம் இப்படி தான் கன்வெர்ட் ஆகுது. சப்போஸ் இட் இஸ் ஹேவிங் சம் கிளாரிட்டி. நம்ம ஃபோனில் பேசும்போது இட் இஸ் ஆஃப் ஹேவிங் சம் கிளாரிட்டி. Suppose what will happen in another system, say 64 kbps தான். If another system, instead of 8 kilohertz, if they are using 16 kilohertz, okay, then definitely what will be the RB? What will be the RB? Instead of 64 kbps, 128 kbps will be there for each user. Appo clarity will increase. So that means RB will increase, clarity also will increase. But what is the problem? You cannot accommodate more number of people. அதனால என்ன சொல்ல வரேன்னா, ஈவன் இந்த டெலிஃபோன் நெட்வொர்க் நம்மளுடைய வாய்ஸ் ஒரு சம் எக்ஸ்டெண்டுக்கு தான் ஆப்போசிட் சைட்ல கேட்குது. அதனுடைய கிளாரிட்டி we can increase still further, but what is the problem? They cannot accommodate more number of user at a time. So you have to understand. Okay, so what will happen if I increase the clarity? You cannot accommodate more number of people. That is the major problem. So again, there must be some common value. So that's why they have mentioned this. There should be some optimization between the clarity and then number of user at a time. So based on that, they have fixed this value practically. Okay, so அப்போ clarity ஒரு வகையில் இன்க்ரீஸ் பண்ணால் என்ன ப்ராப்ளம் வருதுன்னு பார்த்தோம். more number of peoples நம்ம வந்து என்ன பண்ண முடியாது, accommodate பண்ண முடியாது. That is the major problem in the PCM system, pulse code modulation.